Okay, so today we're going to be exploring two ways of evaluating a limit in 0 over 0 form. So the first method, as most people commonly do it, is using L'Hopital's rule for 0 over 0. But before we do that, let's verify that this limit is indeed a 0 over 0 form. So, due to continuity of the function, we can put 0 directly in. We get 2 sine 0 minus sine 2 times 0 over 2e to the 0 minus 2. These two are trivially 0, so no. Sine of 0, 0, so we get 0 over, well, e to the 0 is 1, so we get 2 times 1 minus 2, which is 0. So it is 0 over 0. So we can apply L'Hopital's rule for 0 over 0, and we have to differentiate the numerator and denominator. Let's see. Here's the first derivative. This is chain rule, so there's 2 in front. E to the x doesn't change. Constants are gone. We get this. Let's quickly verify that also leaves us in a 0 over 0 form. So cosine 0 is 1. 2 times 1 minus, well, 1. 2 times 1 is 0. And as x approaches 0, e to the x, which is 1, times 2 is 2 minus 2 minus 0, which is 0. So we indeed have another 0 over 0 form. Alright, so traditionally we'll apply L'Hopital's rule again. Well, we actually have another 0 over 0 form because sine of 0 is 0. So that gives the numerator as 0 by default, and 2 times e to the 0 minus 2 is still 0. So we'll do L'Hopital's rule again. And we see that we've finally got something that is of determinant form. And if we put the x in, we get minus 2 cosine of 0 plus 8 cosine 2 times 0 over 2 e to the 0, which equals, well, negative 2 plus 8 over 2, which is 6 over 2, which equals 3. And after a lot of L'Hopital's rules, we have arrived at an answer of 3. But today I offer another method of evaluating this limit, and that is by using each function's Taylor expansion. So let's refresh. The Taylor expansion of a function, well, centered at 0, which gives us the Maclaurin expansion, is this. And that just means that the function is equal to the sum of the function's nth derivative times x to the n over n factorial. And we sum all that up from n equals 0 to infinity. Basically, this tells us that our function will be equal to this. And if we apply this sigma notation to each function, the limit turns into something like this. This, by the way, is the Maclaurin expansion of sine x. And similarly, we can do it to sine of 2x, which isn't too far off. And e to the x also has a Maclaurin expansion, which is okay, so we've seemingly made this limit more complicated, but I argue that after we simplify some brackets, we get something that will give us the answer directly. So let's analyze the numerator first because that's more complicated. If we open brackets, the first set anyways, we get 2x minus 2x to the power 3 over 3 factorial plus 2x to the power 5 over 5 factorial minus 2x to the 7 over 7 factorial. And over here, I'll open up that bracket. And, well, what we can see immediately is that the first terms cancel out, which leaves us with this. And if we combine like terms of equal power of x, get 6x to the power 3 over 3 factorial minus 30x to the power 5 over 5 factorial plus 126x to the power of 7 over 7 factorial. Sorry about that. And on the denominator, we have something much simpler. Well, if we open that bracket, we get this 2 factorial is 2, it's just x squared, plus 2x to the power of 3 over 3 factorial plus 2x to the power of 4 over 4 factorial. And here we see that we have minus 2, minus 2x minus x to the power of 2. And we see that the first 3 and the rear 3 cancel out. Like that. And there's a limit. That should be an expansion. And, well, for this type of problem, we have a limit x to the power, limit x approaching 0. We compare the lowest power of x. So in this case, for the numerator, it's 6x to the power of 3 over 3 factorial. And for the denominator, we have 2x to the power of 3 over 3 factorial. And since they have equal power, we only need to compare the coefficients. So the answer is comparing coefficients. And this cancels out, which leaves us with 6 over 2, which equals 3, which, as we can see, agrees with our first answer.